Right, so hello again and welcome to the last talk in the last session for this year in the information extraction seminar. We are going to be talking now about relation extraction with matrix factorization and universal schemas, which might sound a little bit obscure to most of you because, well, even if we all know what relation extraction is by now, maybe we cannot understand yet what matrix factorization might have to do with it, or what a universal schema is, but I hope this will become clear during this presentation. So we begin by an overview of the talk. We first present the general setting of this problem, then we move on to some mathematical basis for this. We then present some empirical findings, which were presented in the original paper, and then draw some conclusions from this. So, yes. The main problem in information extraction, as we have understood, is transforming information from a source into a target schema. In this example here, the schema is a relational database schema, as we all know them, and the information source might be, well, database containing information about an online course in Moodle, apparently. Now, if the source is natural language, this poses a problem because it may contain more information than is possible to insert into any predefined schema without altering the schema during the process. Or even worse, it may contain information or knowledge that cannot be put into any schema at all. We have seen several examples of this during the previous presentations. And the solutions we have encountered so far are following. First, we can try to learn a latent schema from the language source. This, well, the word latent here is highlighted because I don't know if everyone is familiar with this use of the word. Is no one familiar with this use of the word? Okay, well, this has to do with, for example, a technique called latent factor analysis, which you might know from statistics, or maybe not. Well, it's a simple idea. It is essentially taking a bunch of observations which contain information on n variables, say, and to try to reduce these n variables to a possibly smaller number of unobserved variables, which in some way explain the variation in these observed variables. It's some kind of mapping of the information to a different space. It is what is done, for example, or what has always been done with IQ tests. The IQ is a latent factor which explains variation of quantity, in this case intelligence, whatever that may be, but well, in the same sense, a schema may be latent in textual information because it is unseen. It is there in a way, but we see it only through its manifestation or through its effects in the form of the language itself. Now, this is the approach taken by OpenIE, as we have seen. And the limitation, the problem with this, is that it cannot generalize in the sense we see in this example. OpenIE can extract the relation Gödel, professor at Princeton, if the text contains information to support this, but it can give us no information about the relation Gödel, historian at Princeton, which is clearly false, which it cannot be true because, well, Gödel was no historian. But OpenIE has no way of providing a quantification of this impossibility for the relation, so to speak. There is also distance supervision, as we have just seen in the previous talk, which is based in aligning relations from a structured source like Freebase with the surface patterns, with the mentions of the relations themselves in textual data. The limitation in this is that it cannot predict this surface patterns, it cannot predict these mentions of text, so it is in a sense also a partial solution. Then the solution presented in this paper, the paper I read, is to simply store all the information available in a probabilistic database with universal schema, which is basically to take a union of all the schemas in our source information and construct a probabilistic database, as we can see in this image, which might be not so clear right now. So let me try to explain it. We see in the columns the binary relations, in this case between entities. The relations here are X professor at Y, X historian at Y, X employee of Y, and X member of Y. These are just examples of rather simple binary relations which might exist between two entities, X and Y, and the rows of this image, of this matrix, are entity pairs which might be or might not be in these relations. We have Ferguson, Harvard, we have Oman, Oxford, Firth, Oxford, and Gödel, Princeton. Now, the disks, the solid gray disks, are to represent relations that are actually observed in our source data. For example, our information in this case contains the fact that Ferguson is a historian at Harvard, or that Oman is a professor at Oxford, but does not contain Ferguson professor at Oxford. The light gray disks are also not observed information, but they are something we would like to have, ideally, as a result of this model. I mean, even if we do not observe the relation Firth professor at Oxford, we would like to be able to somehow infer this, given the overall structure of implication for the two relations. Similarly, even though we do not have the relation Gödel, historian at Princeton, we would like to be able to determine that it is unlikely that this relation is even possible. These numbers, this 0.95 and 0.05, are, well, in a sense, probabilities which the model should estimate. The model we will construct should estimate. Now, asymmetric implicature among relations must be accounted for. This basically means that relations do not always imply one another in a symmetric fashion. That is, the relation X historian at Y usually implies X professor at Y, but not the other way around. If it were true, then Gödel professor at Princeton would imply Gödel historian at Princeton, which is, as we have seen, not the case. And well, since we are taking the union of everything in this case, this adds one extra step. We must map these surface patterns to the relations as they are structured in the knowledge base, the tree base in this case. And well, the final objective should be the prediction of source data and not the modeling of semantic equivalence, which is a much more difficult, maybe even impossible task sometimes. And well, now we can construct the probabilistic model in more detail. We define the set of all binary relations to be this calligraphic R that we see here, for example, X historian at Y. We define T to be the set of input tuples, the input pairs of entities. And we define a pair of relation and tuple to be a relation instance or a fact. We are interested as an input to our model in the set of all observed facts, which we call O. Now we can construct the matrix we have seen in this previous image very simply. It is basically filled with zeros and ones for all the possible combinations of relations and entity tuples. And well, yes, it is easy because we simply go through all the data we have accumulated and assign a 0 or a 1, whichever may be the case for each combination. And we might expect it to look something more or less like this. I mean, again, it's basically a case where everything is either 0 or 1, and for the relations we do not observe, we want to estimate them somehow. The question is how. It's, of course, an important question. And, well, this GPCA, there is already a hint of how we are going to do that. But first, we have to consider what can be done with a matrix. In a sense, does everyone here know what principal component analysis is? Does no one here know what principal component analysis is? Okay, well, it doesn't matter too much anyway. It is a simple idea also, and it's also completely similar to a latent factor analysis. What this descriptive technique does is, again, take a set of m observations and n variables, derive the covariance matrix of this information and try to find the change of variables that again allows us to express the same information but with new variables that are not that are orthogonal to each other, so to speak, and in a sense simplifies the analysis of the information. It has, it is also seen as a minimum square problem here, but can also be thought of as this: taking our information points, our data points, as random observations of a multivariate normal distribution. Then this is equivalent to maximizing the likelihood or log likelihood of our data restricted to a certain lower dimensional subspace. Now, this is of course very good if our information is effectively distributed like that, but that is not always the case. Because, for example, the matrix we have constructed has only entries that are 0 or 1, so it cannot possibly come from any normal distribution. Then, well, there is also a more general form of this technique, which can accommodate any distributions which are members of something called the exponential family of distributions, which, well, as the name implies, are just a group of distributions which have an exponential there somewhere and a series of a vector of parameters, which are in this case called theta. And the idea behind this is that if we are able to transform our data again into this new parameter space, then we can proceed as before and simply maximize the log likelihood of these new quantities, quantities in the new space, and we should have something equivalent to the original PCA. Now, again, this is important because the entries in our matrix are zeros or ones, which basically means that they are all draws from a binary random variable, a Bernoulli random variable, with parameter p or theta or anything. So we can apply this technique to the matrix we have just constructed by simply using the logistic function to transform our information from the zeros and ones observed to this new parameter space. And we will see, well, this is basically the same I have just said, just with an example there. Again, the variable we are trying to estimate is YRT for relation R and tuple T, and we want the probability that it is equal to 1 for this fact. We use the logistic function to estimate this, and well, now we can define our parameter theta as simply this. It is basically the expression we have seen before for the principal component decomposition of the original matrix. This is, in a sense, a general model, because if you remember, our matrix contains both the tuples observed in surface patterns, that is, all the information from text data, from unstructured text data, as well as all the relations contained in our knowledge base. So this model will be able to detect all the relations between one and the other at the same time, which is, of course, very nice. We can also define our parameter to be something like this. It is a local model, which means that this takes, for each pair R and T, for each relation and tuple, it takes this sum over all other or other observed relations except the one we are considering. And these quantities are, as it says there, an affinity or association strength between the relation we are currently studying and all the others. It is basically a fancy way of saying how similar this relation is to any others and what information the others can provide about this specific relation. But well, as we can see here, this model is unable to go beyond the pre-existing relations in the knowledge base, simply because it cannot consider the, so to speak, statistical correlations that might exist beyond this simple linear order approximation. And as a third definition of the theta parameter, we have this. If we observe the relations that are contained in our knowledge base, we will see that they have two arguments in this case, and that they cannot admit any kind of entities in both argument slots. The example here, I think, is quite clear. Hilbert is, of course, was a scientist at Göttingen, but we cannot pretend that the Genselisel is a scientist at Göttingen, or was. Does everyone know what the Genselisel is? Or no? It's a statue in Göttingen. It's a rather famous statue in Göttingen, which, since it is an object, a statue, it cannot be a scientist at Göttingen, even if it is in Göttingen in a sense. So we introduced this definition for the theta parameter of the Bernoulli distribution, and it basically means, again, a measure of compatibility between the entity tuple and each of the, what are they called? The argument slots of the relation. Again, we might expect that this definition gives us, or recovers, valuable information about which relations can admit which entities, and thus allow us to make some form of inference about the non-observed relations. Now, in theory, it is possible to combine these three models. This is what was actually done in the paper we studied, and we will see some results for the three combined models in a bit. But first we have to observe also that there are no negative facts available for this method, because, well, the knowledge base doesn't contain them, and the text data doesn't contain them as well, at least in this case. The way they go around this obstacle is simply transforming or considering the problem to be one of ranking instead of simply trying to estimate the probabilities directly. And well, I'm not going to go into details about this. There are some references at the end. And the idea, well, is basically this. We want to maximize log likelihood, which is terms of the form of this down here. So yes, as I said, I don't think it's important to be very detailed about this. Now, what kind of information today was used for this particular problem? They combined Freebase as a source of structured data with the New York Times annotated corpus as non-structured data. For the New York Times information, they split all available articles. As you can see, articles after 2000 were used as training data, between 1990 and 1999 as test data. For Freebase, it was a 50-50 split. There is also this pre-processing step, this alignment of both sources to be considered. They were simply linked by a string matching heuristic, and this results in about 8,000 tuples for each training and test sets, with corresponding facts in the non-structured data, as well as 200,000 tuples for which both arguments appear somewhere in Freebase, but for which there is no fact in Freebase that links both entities. To simplify evaluation, a subset of 10,000 of these tuples was considered for testing. And well, relations with less than 10 tuples mentioned in text were filtered out because they were considered non-relevant. And well, this again is how we might construct the input data for the model, the observed facts, the set O we had seen before. It is again a union of the observed facts in Freebase and the observed facts in the surface pattern database. That's OFB and OPAT. It's these two sets. And well, I think this has already been explained. As for the evaluation itself, well, they compared against other existing systems. A distantly supervised classifier, newer version of this distantly supervised classifier, which uses preprocessed clustering features. The idea behind this is to allow it to discover some more general relations between data as the original distantly supervised classifier, and a state-of-the-art multi-instance, multi-label system, which is also a distantly supervised system. Now, the authors claim that this model, this universal schema model, is much more faster to train. It takes 45 minutes at most, while the others take 4 or 2 hours, and less data for the second case. And how does it actually perform? Well, we see here a graph that shows the 3 baseline systems just mentioned. The models, the neighborhood model and the latent feature model, the combination of both, and the combination of both with the entity model, as were defined previously. And we can see that, in fact, these 3 latent feature models outperform the baseline models at all recall levels, which is, well, quite good. Here we see again a comparison for only one relation in the knowledge base, and we can see that, well, it says so right there, the 2 distantly supervised classifiers have a significant loss of performance at around 50% level of recall, simply because beyond this point they were not able to incorporate the non-observed information in the test set to improve the estimations, so to improve the classifications for the overall database. The baseline system YA11 overcomes this in a way with the clustered features, but is also significantly below the latent feature models. As for the prediction of surface patterns, well, this is something the distantly supervised classifiers cannot do, so it was there was no point in comparing them to this system. We can see some mean average precision and weighted mean average precision for a few relations contained in freebase here. Again, this is only a subset of the entire results that were reported. I can give you references at the end if you like. The interesting thing here is that this model can indeed capture asymmetry, because, well, I did not include the other relation here, but the prediction for the relation x scientist at y is comparably good to the prediction for x employed by y, even though one is much more general than the other. One would expect, or could expect, that if the system were not to distinguish these asymmetric features, then one would be under-predicted or the other would be over-predicted, but it is not the case. So, well, as a final overview, we can try to review again everything this method does. It takes simple data, two things. It takes structured and non-structured text data. It has to align both text sources. This process is, in this case, done by a string matching heuristic. The lexicalized dependency paths for the non-structured data must be extracted so they can be added to our probabilistic database. The matrix Y is then populated with the zeros and ones from derived from the observed set O. We construct this objective ranking function and maximize this function using some numerical method. In this case, stochastic gradient descent, but anything is equally applicable here. And finally, we use the estimated parameters to obtain the desired probabilities for the unobserved relations, which will be what should enable us in the end to reason about what we have not seen yet in the information accumulated. And the word posterior here is meant to imply that this is a Bayesian method. It means it can, or it has this never-ending learning quality. I think sometimes it's called like that, in the sense that it can continuously update its inferences as soon as new information is available. Now, as far as the conclusions, well, I think the idea behind this method is good. It's a good idea. And the results that are presented in this paper seem to support this notion. But it is also true that this method is, well, quite convoluted. It's quite difficult to understand and to explain and to try to apply. I think another proof of this is the fact that, unlike for the other systems we have seen so far, there is no functioning live demonstration of this technique yet. It's simply a large number of code files. It's Scala, I think. So if anyone here knows Scala and would like to look at it, well, it's available. And also, I think it is not clear at all what could happen if any text source instead of or in addition to the New York Times corpus is used. I mean, what would happen if we use New York Times and Wikipedia or books or anything at all? There is no mention of this in the paper, and I think it is also not possible to imagine what might be the case just from the results presented, because we have no idea of how stable these estimations really are. There was no form of cross-validation reported in the paper, so I think that greatly hinders the ability we might have to reason about the generalization of these results, if that makes sense. Okay, so here are some references for this topic. I can show them later if you like. And questions. Are there any questions about all this?
Professor Paul, thank you. Questions? So you had this nice picture on the PCA with the bars.
Oh yes.
Yeah, this is.
Mm-hmm.
Can you explain it? Was too fast for me.
Yes, actually I didn't really explain the picture, but I will do it now. This is, well, the disks are again a representation of the contents of our matrix Y. Here it's called X, but well, it's the same idea. It's numbers which should be 0 if the relation is not observed in our information, and 1 if it is. The question mark in this case denotes a non-observed relation. It means we have not seen this entry. It could correspond to pocketbooks being parent of Simon and Schuster. Again, here the rows of the matrix correspond to entity tuples, and the columns correspond to binary relations between the tuples. And these columns here, well, they are, how can I say this? They are a visual representation of the feature vectors that were defined in each of the three models, or two at least. I think I can show it now. The latent feature model has these feature vectors A and B, and the entity model has also feature vectors D and T. So, but for some reason, the authors chose to represent these vectors as these bar graphs or histograms. I don't understand why, but that's what they are supposed to mean. And of course, the first row is the initial state of our matrix, and the second row corresponds to what we might expect once we applied the PCA method to this matrix and derived a posterior probability, which in this case is 0.8 for this entity tuple relation fact. Sorry, I got confused. Yes.
Okay, thank you.
Good. Any more questions?
So if you go back to the extracting of the lexicalized forward to the lexicalized dependency path, where you add it to the tuples of observed facts.
It's this, okay.
So you would add, actually, you add the path as an observed fact, or?
Yes, this basically is done, I think, to reduce the unstructured text to a form that is comparable to the database schema that is already existing in Freebase in this case, which means for a sentence like M1 heads M2, we need to extract this.
Mm-hmm.
The
But then you don't know if it's true or not, or how do you know if it's an observed fact and then you assume it's true?
Yes, that is a good point. I think they assume that every observed fact is always true, which I
guess maybe they only extract short parts of this lexicalized dependency part, so they can be pretty sure that it's true. I mean, if you only extract like noun, verb, noun.
no, yes. That's because I assume that if there were a negation or something, this
Then,
would filter it out and would not. Okay, yes.
Okay. So, but then if you want to run it again on some different text, then you need to go through the whole process again, right?
Basically, yes.
Yeah, all the training has to be done again because you have new observed facts in the text, and then.
Yes.
Questions? Okay, then thank you again.